Hello, this is take number 3 of this video. So today I wanted to talk about a project that I was working on for the past couple of months, right? I mean, I left a past couple of months, right? I worked on this project for like a month-ish, and then I left it for like a couple of months, and I'm revisiting it, right? Now, I'm not gonna work on the project today, but I'm gonna just do a very simple tour of this actual project and how it works, right? Now, it's not complete by any means, but I thought I'll just give a tour on YouTube about it. So that's basically it. Now, what is this project about? This project is, um, put it simply, it's just an emulator for the LC3. If you don't know what the LC3 is, it's an instruction set or an architecture, you could say. It's an architecture for a microcontroller family, right? So the LC3 was made for educational purposes, right? And it was made for like hardware students, like electronic students, to like have something to make, some target architecture to make, right? And I'll have info about it in the description below if you want to know more about it. And also, I will also have the repo in the description, the link to the repo. It's an MIT license, so you can do whatever the fuck you want with it, right? So now, let's talk about the actual project itself, right? Now, when we talk about an emulator, we usually have things like state. So we have a certain state, and then we have functions that manipulate that certain state, right? And yeah, so the main state you really have is the machine, right? So the machine is the main state, right? It's the meat, it's the center thing, right? Now there are things that I can do to make it better, and I've already thought of them, but they're not implemented yet, right? So yeah, now let's go through the current implementation. Right, there are registers, right? So each computer has registers, right? Registers are like temporary storage slots where you can store some data, right? And you can operate on them, right? Without things being on the registers, you can't actually operate on them, right? So that's very important to have, right? The registers are very important to have. And in the LC3, you have 8 registers in total, right? All the way from R0 to R7, right? So those are the 8 general purpose registers. Now they're called general purpose, but some registers do have some specific task, right? Like for example, the R6 register is used as a stack pointer, right? To point at the head of the top of the stack, basically, right? But you can technically override the R6 and use it for whatever you want. It doesn't really matter, right? So in that case, it's truly general purpose, right? Now, uh, other than the general purpose registers, we also have the PC, which stands for program counter. And the program counter is just a register which you store address of the next instruction that has to be processed, right? So there's a current instruction that is being processed, and I'll show you what an instruction is and how it's going to be processed, right? But you gotta have to you gotta keep track of the next instruction in line that you have to process, right? So it will keep on kind of processing the instructions as it goes down, right? Now, if you look carefully, you see that the registers use word as a type and PC is uword, right? So what's the difference? If you look at the definitions of word and uword, word is just an int 16, right? It's just a 16-bit integer, and it is signed, right? It's a signed 16-bit integer, right? Whereas uword is unsigned. It's just the same thing but unsigned, right? And in the binary world, a word is usually just 16 bits, right? So that's why I use the term word here, right? Now, why do I have two types? Well, it doesn't really matter. Technically, I could have just used one in all the slots, right? I could just use one for everything. I could use uword or word, right? Technically, uword is more correct because the computer doesn't really care about the sign. Like the sign isn't really something it cares about, right? All it says is zeros and ones, right? So technically, you don't need the sign aspect of it at all, right? So technically, uword would be more accurate. But when I print this machine, right, I want it to print with the sign, right? So I just set it to word, and so I can see the sign as well, right? Because this computer can handle signs and stuff like that. So that's something I have to take care of, right? So that's basically it. Now, then the next thing we have is the PC, right? Which you talk about. It stores the address to the next instruction that has to be processed, which is uword because addresses cannot be negative, so it doesn't make sense for it to be word. PSR is just registers with a bunch of flags in it, right? Now it right now it has 4 flags, and that's basically what the main spec suggests you to have. It only has 4 flags, but I know Some variants of the LC3 have more than 4 flags. They have 5, 6 flags, right? Um, so yeah, I mean, yeah. So it's also a 16-bit wide register, so you can have 16 flags in them, right? Um, 4 of them is already in use. You can use 12 of them for whatever you want, right? If you want to use some fancy trickery or something like that, right? So that's basically the machine. This is the state of the machine, and that's important, right? Now, one thing I can actually improve on this is by having another instruction, or not an instruction, another register called IR. Now I'll explain why that would be better, right? But for now, we're just gonna go back to the previous changes. Okay, so now that we have a basis of what the machine is, let's talk about the actual memory, right? Because memory is important, right? The machine talks to the memory, and the memory talks to the machine, and then that's how things go. So the memory is very simple, right? Now, in a in a 16-bit computer, if your program counter is 16 bits, which in this case it is, you can only access up to 65,000 ish slots of memory, right? So you can only have about 65,000 slots of memory, right? That's the maximum size, right? Now, the reason why I say slots and not bytes is because of another issue that we have right now, right? Which I have to fix. But yeah, so for now, just we can only address up to 65,000 address, right? That's the maximum address we can have, right? But there's no actual limitation on how big the slot can be, right? Now, most conventional computers have one character as a slot, right? And the reason for that is, uh, it just makes sense. I don't know if there's a specific reason. It just makes sense. That's basically the best reason I can come up with, right? There are a lot of things that are defined, right? Now, Now that might change later. Hey, maybe having a larger slot is better. I don't know, right? But that's how memory works, right? One slot is one character, right? But in this case, it's a word. It's a whole ass word, right? A word is 16 bits, so it's double of a character, right? Now it does work, right? This works. This is meant to work with the word, right? It makes things a lot simpler because when we fetch things, fetch an instruction, for example, I can just straight up fetch one block because instruction is also 16 bits. So I can just straight up fetch one block and that's good enough, right? But if we change it to car to match what conventionally is used, right? So instead of your word, if I make it car, now things are not going to go that well, right? Because an instruction is 16 bits. A character is just one byte or 8 bits, right? So that's half of the 16 bits, right? So that means an instruction will have to now be placed on two slots instead of one, right? Which means I have to do two fetches. So I have to fetch two blocks of data and then I have to smush them together in order to form a single instruction. Not just an instruction, anything related to fetching or storing or anything related to just interacting with memory now requires more thought, right? So that's the reason why I've left it like that, but I'll probably change it later. So that's basically the memory, that's the machine, that's basically the definitions of those things, right? I'll talk about the actual function that executes the instructions, right? Now this is the reason why I want the machine to have an IR, word IR, right? This is why, right? The reason is because this function that we see right here, right? It takes a machine, it also takes an instruction, and it takes a pointer to the memory, right? So by having a instruction register inside the machine, I don't have to pass instruction here at all, right? Now it's not that big of a deal. It's not really that big of a deal, to be honest. But that's one thing that I can do basically, right? It would definitely be a better design because most hardware implementations also have an instruction register, right? So maybe it's a good idea, maybe it's a bad idea. I don't really know. So that's that. Now, how do we grab the operation code, the opcode from the opcode from the instruction, right? Because the way the instructions are actually encoded. Let me Let me go to info. There it is. Right. Yeah. So the way the instructions are actually encoded. Give me a second. Um, mhm, I don't know what I'm doing. Okay. So there it is. Okay. Okay. So okay. So the way an instruction is encoded is in the following way, right? So the instruction is 16 bits long. The first 4 bits, the higher 4 bits, are for the operation code, right? So the first 4 bits are used for the operation code to know which operation the instruction is for, right? Then the rest is 12 bits, right? As you can see down here, 12 bits. The rest is 12 bits, and 12 plus 4, that makes 16, right? And the rest of the instructions, they are processed differently based on what the instruction is. So the first step is to actually figure out what operation it is, right? So that's the first thing you have to do. Then based on what operation it will then give you enough information to actually understand the rest of the instructions, right? So if you go over here, that's what we're doing, right? So we're taking the instruction, we're ending it, we're bit masking the top 4 bits, then we're shifting it to the left by 12, right? So we're shifting it by 12. That would put the operation code in the bottom 4 bits, right? So we'll basically give you the opcode. We put it in this uh, variable called op, and we cast it. So technically this is a number, right? But I cast it to this enum, right? In C, an enum is just a number, right? You can cast it. So I basically casted the number, right? A number in normal integer into this, right? So I basically casted that into an enum, right? Now in the enum, this is all the lists of all the instructions in the architecture. There are only 16 instructions, as you can see. In fact, one of this specific instruction, the 13th instruction, is not used. It's reserved, right? So the OP res stands for reserved. And all these instructions are put in sequential order of their real op IDs, right? So I can just take the number and cast it, and now I have an enum value of the opcode, right? Now the reason why I use an enum is so I can switch on it, right? Because there's so many instructions, it's better to switch on them instead of actually just uh, you know manually do if statements, right? That could cause a lot of problems, a lot of headaches. So this is very simple. You just take the op and switch on the op, and then you have all these cases. In fact, the compiler tells you what cases you missed, so that's very good. Now the rest of the instructions, this part of the instruction is pretty important too, right? So the rest of the instruction goes into this variable called rest, right? We basically just mask out the bottom 12 bits. We don't have to shift it because it's aligned properly, and that's it. That's pretty good, right? Now let's actually get into the weeds of things, right? So how the thing is actually implemented, right? So now I'm probably not going to go over every single instruction, right? Probably won't, but I'll go over some of them, right? For example, op br. Br is a very simple instruction. I mean, it's not really that simple compared to other instructions. What it does is it can receive certain Boolean flags, right? And based on the Boolean flags and the flags set on the PSR, so if we go back to the machine, there it is. So when we go back to the machine, you know there's a PSR, right? PSR has all these different flags. In fact, I can tell you what flags it has. PSR, there it is. Mhm. Cannot find it for some reason. That's not where the PSR is. Okay, so PSR has 4 flags, right? The first flag is the negative flag, right? So depending on the previous instruction, before the BR instruction, the previous instruction, depending on the result of the previous instruction, these flags are set, right? So let's say you use the add instruction to add 2 numbers from a register, right? Now, actually, I think this is a bad instruction to explain for the first instruction, so we're not going to explain it. Okay, I'm going to actually explain the next instruction, that instruction, right? This is a lot better to explain. Okay, now this is slightly complicated, but it's not that hard, right? So when you actually have the add instruction, there are two methods to add, right? The first method is adding two. Uh, the first method is actually adding two registers together, right? So if you have register R1, which has a value of 2, and register R3 with value of 5, you can add 2 plus 5 and get the result of 7, and you can put that into another register, which is called the destination register, and you can put it into another register if you want, right? So that's adding two registers. Also, you could add an immediate value to any register, right? So for example, if you have a register um, or 6 and it has the value of 0, for example, right? I can actually encode a 5-bit number inside of the instruction that will be added to the register, right? So I can add, let's say, 5 encoded inside of the instruction, and that 5 will then be added to the R6 register, and then that result will be taken and you can put it to any other any other register if you want, right? So there are two methods you can actually use for adding numbers, right? So the first method is add im, which is add immediate, and the second method is add reg, which is adding two registers together, right? So how do you know which one to do, which one to do, right? How do you know if you want to do this or this, right? Now that is defined by the fifth bit from the left side. 1, 2, 3, 4, 5. The fifth bit from the left or the right, not the left. Um, this bit right here defines the actual instruction that has to be performed, right? So we take that bit, we mask it, we mask everything but that bit, and we compare it to 0, right? If it is 0, right, then this bit is unset, which would make this flag false. If this bit is set, then this will not be equal to 0, uh, which will make this flag true, right? And we can just do an if else on the flag, and then we can do the specific one, right? Whatever you want, right? Whichever instruction you want. So if the flag is set, you do the immediate operation. If the flag is not set, you do the register operation, right? The register one is a little bit easier. Actually, let's do the immediate one first. Okay. Now technically don't need this unsigned in, but whatever, it doesn't really matter. Okay. So so these three bits, right? These three bits, which is 9 bits from the little side, the smaller side, right? These three bits define the register that is gonna take the result. That's gonna hold the result, right? It's called the destination register, right? It's basically where everything is. Uh, it's basically where you take the the result and you put the result in that register, right? A specific register. It's called the DR or the destination register, right? And the next 3 bits is SR, right? By the way, the reason why it's 3 bits is because there are only 8 registers, right? And 8 registers can be defined by 3 bits. So you only need 3 bits to define any register in the machine, right? So you can target any register you want using 3 bits, right? So that's how they're encoded. The next 3 bits are the source register. So one of the registers that the contents is going to be added to, right? So you take the source register, then the last 5 values are going to be the immediate value that you're going to take, and you're going to add the immediate value to the source register. We're going to add the values together and put the result in the destination register. That's basically what's going to happen. It's very simple, right? So we do that exact thing here. We first extract all of those things, right? Then what we do is we calculate the result by taking the machine's, right, register source ID, right? Then this function that sounds sus, right? I should have named something different, but this is sign extend, right? The reason why you have to sign extend something is because it's a uh, 5-bit value, but it's also signed. It's a signed 5-bit value, right? And when you want to add signed 5-bit values to any other value, you have to make sure to extend the sign, right? Now, the function itself is very simple, but if you don't know how sign extension works, this function might just well feel like magic to you, right? It won't really make sense, right? But it will basically just extend the sign to make sure that the sign is correct, right? The value is correct, basically, right? It will add those two things together, right, into this intermediary result, and then we're going to basically, well, we could have done like that. It doesn't really matter. It's the same thing, right? Then what I do is I take the result and put it on the destination register, right? Pretty simple. Then I set the flags, right? So the PSR that has the flags will have to change because the result might be negative, right? If the results are negative, the n flag, the n flag will be set. If the result is 0, the 0 flag will be set. If the result is positive, the p flag will be set, right? And we have to set the flags appropriately, right? So that's basically how we're going to do it. We're going to use this function that's going to take the machine, the result, so whatever result you have, right? And based on if the result is positive, first it will check if the result is 0. If the result is 0, it will set the 0 flag, right, using this set flag function. The set flag function takes the pointer of the machine and then the boolean for n, z, and p, right? So you can see the middle boolean is for z, for the 0th flag, right? So if the result is 0, the 0th flag is set. Otherwise, uh, uh, otherwise, if the top bit, the sign bit is set, right? If the sign bit is not set in this case, I don't know why I did like that, but the sign bit is not set, then I will make it positive, because if the sign bit is set, then it's negative. If it's not, it's positive, right? Um, or else, right? If none of those match, then this one has to match. Else, it's a negative value, and one is going to be set. And the negative flag is going to be set, right? That's basically it. That's how it works, right? Now the register add does the same thing, but instead of extracting the second operand from the immediate value encoded inside the instruction, it'll actually have a register ID, right? So now we have two source registers, right? Source register 1, source register 2, right? You add those two together, which we do right here, right? Well, this is and whatever, right? Give me a second. Yeah, this is add. So we add those two together right here. So we extract the encoded registers, right? And we add them, we calculate the result, and then we put the result and then set the flags, right? That's basically how that works. Now I don't know, for some reason I really like this. I don't know why. Maybe there's a reason. I don't know, right? So that's basically how this thing works. Now I think I'm gonna stop recording for now, right? I'm probably gonna make another video on it. Uh, yeah, we'll see. But if you want to know more about the project, links in the description. But yeah, thanks for watching. Peace out.